All right, so the last thing we have to talk about before midterm is data representation. How do computers read our data? If you think about it, right? How do computers know the data? All right, let me ask you another question then. If I want to send you a character A, right? How do I do that? I mean, because we are human, I can say, hey, you understand that. The computer doesn't understand that. Why? At the end of the day, if you kind of zoom down to the lowest level, right? What can the computer measure? Because the fact that you can understand my word and the letter, the alphabet A is because you have the hearing mechanism, like in your ears, to process the sound wave coming in. Then you can recognize how the letter A is different from the letter B. It's different from the letter C. And you can then put together a word, right? Which means that I can talk to you, which is what I'm doing right now. Does the computer have this complex ability to sense things? Not really. It does have a pretty complex ability to sense, right? But it's a different way to sensing. What is the signal inside your computer? What's the type of the signal that goes on? Zeros and one. Why? Electric signal. You plug your computer on. Basically, it's driven by electrons, right? What's the easiest way to measure things? How about I say it this way? Because I don't know if I how fine tuned I can measure things. If I say 0 volts, I'll say that's 0. If I say non-zero volts or something like say greater than 1.5 volts, I'll say that's the number 1. Is that easier? I'll just think of it this way. I have a voltmeter, measure the voltage value. And if I see something non-zero, that's a 1. If I say 0, that's a 0. Can I do that? Because computer built on electrical circuit, right? It means that if I want to measure something, I can just have the way to measure the voltage and look at whether it's a 1 or a 0. Why is it so important that I need to know is that a 1 or 0? Because from there, I can have the series of ones and zero and convert that to a decimal number, 10, 20, right? If I measure like 1, then 0, then 1, I can say that's 101 in binary, which is what number in decimal? 101, 5, right? So I can do the same thing. If I measured number 65, whatever sequence of 101, like 1 and 0 is, like it's 1, 0, 0, 0, 0, 0, 1. That's basically 65. If I said correctly, I'm not sure. But once we have 65, say, hey, let's assume that's an ASCII number. So it's a letter A. Right? Now you can process text. And now that you can process text and you have the compiler, what does it mean? Yeah, you can then understand, first of all, any language data. Second of all, your program. Because your program is in plain text, English, alphabet. Convert that using the compiler. I get bunch of 1 and 0, going back to the basic. I can then measure 1 and 0. I'm good. I can run my program. All right. And the fact that you can send this 1 and 0 in sequence, right? 1 and 0 in sequence, then you can measure a number. That's why you can basically represent your data, right, in binary. So a quick recap. How do I represent number in binary? All right, quick question. How do I How do I convert 10100 into decimal? Start from right to left. Okay.
2 to the power of
Start. Right, okay, so this is 0 multiplied by 2 to the 0 plus 0 to multiply by 2 to the 1 plus 1 multiplied by 2 to the 2 plus 0 multiplied by 2 to the 3 plus 1 multiplied by 2 to the 4, right? Any question about this? Okay, so let me do a little bit of a conversion. You remember decimal like 4, 5, and 6, right? How do I do the conversion into um, okay? How do I factor this out? This is basically 4 multiplied by 10 to the 2, right? Plus 5 multiplied by 10 to the 1 plus 6 multiplied by 10 to the 0. This is the same logic as how can I write 10100 in binary, right? Every single digit in the binary, you add 2 to the n as a factor into that digit. This is similar decimal. So in decimal, instead of multiplying by 2 to the n, you multiply by 10 to the n. Every time you have one additional digit, it's 10 to the n plus 1. So you start with 10 to the 0, multiplied by the last digit, which is 6 in this case. Right? So it's 6 multiplied by 10 to the 0, plus 5 multiplied by 10 to the 1, plus 4 multiplied by 10 to the 2. In binary number, we just change the base from base 10 to base 2. The digit work the same way. I have now the digit option is 1 and 0. And that's it, right? So that means I can convert binary to decimal. How do I do the reverse? How can I say convert number 17 to binary? The what? So my trick is I would factor this number based on the multiple of 2. But because I do this a lot, it's not always convenient. The other way is I keep dividing this number by 2. The first time I divide by 2, I just write the remainder. So I divide 17 by 2. What do I get? Remainder of 1 and result is 8, right? So I write the remainder, I write it back. Then I keep dividing. So 8 divided by 2, what's the remainder? 0, that's 4, 0, 4, 2, that's also 0, and you have 1 left. When you have 1, you divide by 2, what do you get? 0, remainder is 1. All right? So that's 1, 0, 0, 0, 1 in binary. Okay? Most of the time in this class, your conversion actually will sometimes be in binary to decimal because you want to convert binary into something like a character so that you can change to ASCII number. Sometimes you want to change from a binary to and from hexadecimal because in computer science we use hex number all the time. It's kind of like think of it as a short form for binary number. It's much more compact. Why do I say it's a short form of a binary number? So let's say I have a hexadecimal number 0x BCD, right? These are valid hexadecimal numbers. How do I get a binary out of this? I mean, the obvious way is I can convert to decimal by D is what? A is 10, B is 11, C is 12, D is 13. So it's 13 multiplied by 16 to the 0 plus C is 12, so it's 12 multiplied by 16 to the 1 plus 11 multiplied by 16 to the 2. And add them up, that's the decimal number. Then you convert that to binary, right? Anyone has a better trick? Yes. Yes, exactly. Each letter here is a 4-bit binary, right? 14, my bad, 13 is what? 1101, right? So BCD is basically, this is 1101, C is 1011, B is 1013. Am I wrong? I think I'm wrong. Ah, thank you. All right, so C is 1100. Sorry, I minus one. Somehow I actually did minus two. So your binary number is 1011, 1100, 1101. If you have a random binary number in that case, then let's say you have this. What you would do is you group this by 4 at a time, 4 digits at a time. 0110, that's 6. 1010, that's A. 1011, that's B. And 1 is 1. Right? So you know it's 1BA6. So group by 4. If you have binary, you can convert to hexadecimal really quickly. If you have hexadecimal number, just break it down for each alphabet. You get a binary set of binary. Yes. How do we convert from hex to binary, right? Because you know that each digit in the hexadecimal number is 0 to 15. That's exactly 0, 0, 0, 0, up all the way to 1, 1, 1, 1. Right? So you convert each digit to a binary number. Then you plug them after another. You basically write them all. So that's kind of like a quick recap on binary number, hexadecimal number, decimal number, right? So now my next question is, how can I talk to a computer? All right, because that's quite important. First of all, the computer doesn't really understand your command, right? You can't just say, hey, add this and this to my laptop, and it will do exactly that. You actually have to write a program and somehow convert to a binary number, which ended up being do the add instruction, add X and Y in binary, right? Why the binary format, as I said earlier, because you can easily measure the voltage. And the way it works is this, right? So on your computer, you basically have this reference voltage. You have a reference voltage, which is your supply voltage. It's the voltage you supply to the computer. For example, some logic would have the supply voltage of, say, 1.5 volts, right? So that's the maximum you can go. What I would do is I would measure this voltage. If it's in this range, that's the number 1. If it's in this range, that's the number 0. That's it. I measure the voltage of my logic. If it's like 1 volt, that's number 1. If it's 0.3, number 0. This allows me to convert something that might have some noise, basically some electron lying around, which measures a little bit of voltage. It doesn't matter. It's less than 7.5. That's the number 0. It allows me to measure this and convert the voltage into 1s and 0. Right? And you know the clock, right? When you buy a computer, you might have realized your CPU operates under certain clock. The clock speed. The clock speed is the speed. If you think about it this way, every time I clock, I measure again. That's the next binary value, right? Do you know? Have you heard of Morse code? How does Morse code work? That's like a short and long signal, right? And you combine that together into a letter, and a bunch of letters combined to a word, right? And the way you send one portion of the code is like you either quick tap or long tap, right? So you choose to do quick tap or long tap, and then you do the next one. The same thing here. You measure the voltage, clock, measure the voltage, clock, measure the voltage, clock, measure the voltage, clock. That becomes 10111 or whatever number you read it. Right? It separates the first part of the information to the next part of your information. Now the idea is, right? Now the idea is, computer can read binary because I can measure the voltage. Now you can also write program. Hopefully, you can write program in C, right? It means that you somehow can write text. that looks like a C code that can run, then my job is to make sure that your program is now understood by the computer. It means that the compiler transform your program into some binary that the computer will know, right? So at the end of the day, your commands are in binary, your data are also in binary. We will talk about this in module 3 when we talk about assembly. How do we understand the command in binary and what does it mean to do things? What does it mean to run a program? A much simpler thing that we are going to learn right now is, if I have a data, how can I know and figure out that that's a character, that's a floating point, that's an integer, right? An integer number would work in a different way as a character. All right. And we use this as the interface between your assembly code and a computer to run the code on. So everything is about representation. How do I represent data? We have data as an input, data as an output, and each program also has its own view of the address location as well, right? We will use this concept also for the virtual address, which we will learn in module number 4. When the program runs, right, it's gonna determine where your data is gonna be, right? So one thing is, to understand the data, you might have then realized by now your data has different size. Some data is 1 byte, some data is 2 bytes, some data is 4 bytes, right? So if I want to print an integer, it needs to know that I take a 4-byte chunk and print that, not just 1 byte, not just 2 bytes, right? I need to know that it's an integer and it's supposed to take 4 bytes. In a computer, there's a definition called a word. It's a unit of data. Your 64-bit machine use 8-byte word. The word will be the size of your address. Is the size of your address. What does it mean? A pointer is the pointer store an address, right? It means that the pointer is 8 bytes in size in your 64-bit machine. 4 bytes. You might have also heard in a 32-bit machine, your address can go only up to 4 gigabytes, right? The reason is, if you try to get the value of your address, which is only 4 bytes long, 2 to the 32, 2 to the 32 is essentially 4 gigabytes. You can't have any memory bigger than that because your pointer cannot point to that location. It just doesn't fit in 32 bits anymore, right? So this is a unit in which the hardware can use to also transfer the data as well. Physically inside your hardware, many things are done in this 64-bit chunk. Even though you want like 1 byte at a time, they might transfer like this 8-byte chunks for you. Different architecture support finer cluster grain. Sometimes you can specify to the computer, hey, don't give me the whole 8 bytes. I only need 1 byte. Give me 1 byte and that's it. All right. So you can define the hardware that way. And memory address. You point to the exact byte. All right. You point to the exact byte that you want to access. Your pointer points to the exact byte that you want to access, right? So one thing you know for sure from the sample code we did already through the pointer exercise, that I can create an integer pointer, cast them back to a character pointer and go 1 byte at a time through your integer data, right? But your address will always point to one of the bytes, right? It always will point to one of the bytes. In C, you can use %p print the value of the pointer and %f to print a hex number. All right. So if you want to print the value of the pointer, use %p. Now here comes the first confusion. That's this concept of big versus little endian. All right. How big is an integer? 4 bytes, right? One integer, huh? Yeah, 32 bits, 4 bytes. All right. Uh, let's say you have a machine that has to, if you want to send a data to another server or something, right? And I want to send an integer, it means that I will need to send 1 byte at a time, if you will. I just place 1 byte at a time so that the other side receives my data, right? But the key issue here is, do I send this guy first or this guy first? All right. Because each machine might work differently. If I send the left guy first, and the target machine did not know that, and they assume that, oh, okay, whatever I see first is the right guy, you get a totally different data, right? You will read a different data. So this is what big and little endian come into play. So big endian, it means that the least significant bytes. So now let me define a new terminology. How many of you hear this before? Least significant bytes. All right. So what does it mean? Yeah, great job. Basically, in your integer number, you have 4 bytes, right? If you flip 1 and 0 in each of the position, you change the value in a different way. The last bit, if I flip from 0 to 1, the value changed by what? 1. The other side of things, if I flip from 1 to 0, what's the change in my value? 2 to the 31. So we call the other side the most significant bit, because if I flip that, my value changed entirely. And I call the least significant bit to be the lowest bit, which is if I flip that, yeah, the value changed by 1 or 2 or 4 based on the position, right? But these are the lowest significant. So in the big endian machine, like a network protocol, when you want to send things over in a network, the highest address that you're in the 4 byte range, right? So this is like, each of these will have its own address because address point to individual bytes. So the highest address will be in the least significant byte. For little endian, the least significant byte store the lowest address. So it's always at the least significant byte, but is it the highest address or the lowest address? Now that some architecture like IA64 or ARM or Alpha will support both formats. Some architecture like the older version of your x86 Intel and AMD CPU only support little endian. Older version of ARM also support just little endian. Network protocol go with big endian because that's when they design it and they have to make sure your internet still functions. All right. So here's an example. So let's say you have a value of 1, 2, 3, 4, 5, 6, 7, 8 in hexadecimal. Now that's your integer. 0x in front of anything means that's a hex number. Sorry about that. When I write 0x, it means that's a hexadecimal number. It's not a decimal number. So the hexadecimal 1, 2, 3, 4, 5, 6, 7, 8. A convenience thing about hex number is each 2 digits is exactly 1 byte. Integer is 4 bytes, right? This is 1 byte, 1 byte, 1 byte, and 1 byte. Why is that the case? Because 2-digit range is from 0 to 255. 16 squared minus 1, that's 255, right? So that's exactly 1 byte long. It's like eight binary numbers. So for the little endian, again, where is the least significant byte? Is it 7, 8 or 1, 2? The least significant. 7, 8. All right. If I change from 7, 8 to 7, 9, my value changed by 1. If I change 1, 2 into 1, 3, my value changed a lot more. Right. So now the least significant bytes is at 7, 8. In the little endian, it means that the byte 7, 8 also point to the lowest address So let's say the address of the X pointer that point to this number is at 0x10. I print the pointer out, it prints 0x10. It means that this address span from 0x10, 11, 12, and 13, right? So this is a 4-byte data. So it has to be from 0x10 to 13. It basically means that 0x10 has 7, 8, 0x11 has 5, 6, 0x12 has 3, 4, and 0x13 has 1, 2. For the big endian, it's the reverse of that. So 0x10 point at the highest significance, which is 1, 2, followed by 3, 4, followed by 5, 6, followed by 7, 8. Any questions? Getting stored in this process. But one did have its own values. Oh, okay. So the question is, if I write 0x in a program, right, it will also know that's a hex number. It depends on how you would write it. Each language, each programming language would treat this differently. So the compiler, which is responsible for understanding your code and what it do, it detects this and says, oh, okay, I will treat this as a hex number, so I will convert this to the value that it represents. All right. So now I want to make sure that you all have this clear distinction. The data type and the value that go into the data type. All right. The value, think about it this way. The value is what it the value is what it represents. All right. And the value of 65 in decimal represents the number 65. The same value in a different base number, like a binary number, the value is the same. It's 65. It just represents just a bunch of ones and zeros. All right. So when you pass in the integer value, I got a lot of questions from the students for every single semester, right? Is this a binary value or a decimal value or whatever? It's the same because it has the same value. It's just a representation when you print it out that matters. So in the printf, if you want a hexadecimal number, use %x. If you want decimal, use %d, but it's the exact same number in terms of its value. It's the same data that has exact same value, but it shows in a different format. Yeah. It's like when you have a Morse code that say I am here, right? You can say I am here, or you can have the whole Morse code that represents that thing. It's the same data, but in a different format. One is Word, the other one is Morse code, right? Same thought process. And now you have the data type, right? So let's start with something simple. How do you represent a character? ASCII table, right? You use it already in assignment 2. It's a format that maps the value between 0 and 255 into a character. So that's 1 byte. Your string representation is basically then a bunch of characters string together, right? Each character is encoded in the ASCII format. And then it has to have this null value, which is number 0. At the end of my string, it would tell, okay, if I want to do printf on a string, and if I keep reading and I see 0, I know that, yeah, that's it. That's the end of my string. For example, Syskill, right? You can represent it using SYSKILL followed by number 0. You know that if I want to print this, in DRAM, it literally will look like SYSKILL and then number 0. And whatever comes after it, I don't care because I know that's the end of my string. The other simple representation is an integer. Okay. We can represent integer using binary. Then the number of bytes in the integer tell me the maximum and the minimum number I can have for the integer. For example, if I have 4 bytes, it means that it can only cover the range 0 to 2 to the 32 minus 1. So that's the number of integer I can represent because I have limited range. In ANSI, like the ancient version of C, short integer is 2 bytes, integer is 2 bytes, long integer is 4 bytes, long is 8 bytes. In the modern version of C that you guys are using right now, integer is 4 bytes, long is 8 bytes still. All right, and short is 2 bytes. Okay, any questions so far? As I said, the size of each data type can change based on the version of C you're using, right? ANSI C, as you can see, is integer is 2 bytes. So use the command size of to check the size of your data type is generally is an okay thing if you need to make sure you get this exact number of bytes for your program. Now here's a complicated question. How do I represent a negative number? Any idea? Okay, so your proposal is we should have one bit that say if this bit is 0, it's a positive number. If this bit is a 1, it's a negative number, right? All right, so let's go with that, right? So I would say I want to make sure one of the bits become what we call the sign bit. The reason why we call this a sign bit is that bit determines the sign of that number. Is it a positive sign or negative sign? Okay. And your modern day integer can be unsigned or signed. Any question about unsigned number, every bit is a positive number. So you convert binary to decimal value. Whatever number that becomes a decimal value and clean. Really easy to convert. Okay. The sign bit, what we use today is what we call the two's complement format. Anyone heard about this before? Okay, there's multiple knots here, which is awesome. So the way two complements format works is this. You break your number down into multiple bits. So that's, let's say that's your integer. The most significant bit, you convert from binary to decimal the same way, but you multiply by -1. The rest is a positive number. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 9-digit binary, right? So if I do this logic and let's say the number is 1, 0, 0, 1, 1, 0, 0, 1, 1. What is my value? I want to convert this into a decimal value, right? So the way I would do this, I said, hey, the topmost digit, whatever that value is a negative number. So it's 1 multiplied by what? Should be 2 to the 9, I think. If I 2 to the 9, right? There should be 10 digits here. So it's 1 multiplied by 2 to the 9. And I say that that digit has to be negative. So it's -1 multiplied by 2 to the 9. Plus, I convert the rest normally. So what's the rest? 2 to the 6 plus 2 to the 5 plus 2 to the 3 plus 2 to the 1 plus 2 to the 0. The value is I combine those two together. So that's the value of my sign to complement format. Again, to quickly do this, the most significant bit is a negative number, the rest are positive numbers. And there's actually, how many people are asking, why do we have this complicated format? Why can't I just say if that bit is a 1, it's a negative number, the rest is just whatever number I multiply -1. Beyond the byte. Basically, this allows you to, so here's the range of what you can represent, right? let's say that's your integer range, 0 is somewhere in the middle, and you can keep adding 1 to this. You keep adding 1 to this. You go to the positive maximum, which is 0, and then these are all 1s, right? 0, and then 1, 1, 1, 1, 1, 1, 1. If you add 1 to this, what happens? It becomes 1 and then all 0, right? So that's a negative maximum because you have a negative 2 to the 9 plus nothing, right? So it goes from here. If you add 1 to this, come back to negative maximum. And if you keep adding 1 afterward, rotate back to 0. These kind of allow easier conversion between a positive and negative number. Another thing that's quite neat is in this format, if you have the number x, if you have the number x, and if you want to get negative x, one trick that the computer can use is I do the not of x, I flip all the bits and then add 1 to them. That will give me negative x. And we use this a lot whenever you see a minus b, because that's a plus not b plus 1. Right? That's a plus not b plus 1, which means that I can build a subtractor. I subtract two numbers using an adder. I only build logic to be able to add things. And then I do not b plus 1. That's it. I can subtract. All right. So in C, you can write unsigned constant by having the uppercase U at the end of the number. That will say, hey, represent that number as an unsigned. All right. And now here's the interesting question. What happens when you mix the two types? What I mean is, let's say I do int A and then unsigned, int B, and afterward I do A plus B. So here, if I do that, the sign value first convert to unsigned. So you don't have the assigned bit anymore. Whatever bit you have, it's like 1, 0, something, 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 that become unsigned. You add two unsigned number. Whatever result becomes the type of the new variable. So let's say if you do C equals A plus B and C is a signed number, you change A to sign, you first change A to unsigned, B to unsigned, add them together, convert to a signed format. And here is what I really, so here's my key message, right? Here's my key message. Try not to mix them. If you want to mix them, you better know that you're mixing them and you cast them properly first before you add the number so that whoever picks up your code can know, okay, yeah, there's a weird unsigned plus sign thing here. And I know that's an unsigned, that's a signed number. I can develop my code afterward, being aware of that. All right, so it's always safe to casting into the type that you want first. Try not to mix the two types. All right, any questions so far? Simpler to think about if you don't need a negative number. I mean, there's a lot of cases where you don't need a negative number, right? And that means you have one extra bit. You can work with your number range double. This is fun part, extension and truncation, right? So if I have a negative sign number, if let's say I have a negative character, a signed character, negative 128. That's going to be 1, 0, 0, 0, 0, 0. So that's negative 128. 2 to the 7, negative sign, the rest are positive numbers. I want to extend this to a 2-byte sign number. How do I do this? The way I do this is I just keep adding 1 to whatever size it is. I just keep adding 1, and it's going to be the exact same value. it's going to be the exact same value. The way this works is that's another beauty of the two's complement format, because you can extend number of ones and you still get the same value back, negative 128. Because whenever you extend one from it, it's basically your old sign becomes a positive number, right? This bit suddenly becomes a positive number, and this becomes a negative number. If you add the two up, it actually equal to negative maximum. So whatever you do here to extend the number one, the value doesn't change. The value doesn't change. Truncation, that's the bad part. If you have this number and you convert to a character, it actually cut up the bits. So your value can change. You can extend from integer to long integer. Everything would work the same way. Short integer to an integer, everything would work. An integer into a short integer, it might not work. All right, just be careful. It might not work because you basically cut up the bits.
Short to long.
Short to long also work as well because that's extension. Basically, the extension work, truncation doesn't work the same way because you basically cut up the bits. If you want to do int to short int, hash the int to short, and hopefully your number range is within the short int, not bigger than that. Because if it's bigger than that, definitely the upper bit gets cut off. Summary, extension yields same result. Truncation can change the value if you actually need to use the upper bits that you cut off. Right? What it means is, let's say you want to cut from this, you cut here, so you just want this, right? And say your number has some ones in here. That thing is gone, right? So your number will change, the value will change.
Could you show an example going to convert a negative form?
How about we do a sample code after this? Does it feel like that would clear things up? All right, because I think this is basically the last part. That's why I said let's do sample code afterward. Because the last thing is the floating point, which is likely the more complicated one out of the integer, character, and everything, right? The floating point, the way it works is it's based on this IEEE 754 32-bit floating point format. The way it's defined is that's your number. The top bit is the sign bit. The way the sign bit works, unlike integer, this is essentially, if it's a 1, negative number. If it's a 0, positive number. The whole thing is a positive or negative number, and that's it. All right, there's no two complements here. It's just, if that bit is a 1, whatever I do here become a negative number. I just multiply the whole thing by negative 1. Okay, so that's the sign bit. Then there's two more chunks to this. There's the exponent bit. This is a mantissa bit. For the exponent bit, you take those bits out, convert to a number, then you do this. You multiply your total by 2 up to the e minus 127. So this is e. You convert exponent, whatever 1 and 0 in there becomes e. You subtract 127 from that, and you multiply your results by 2 to that number. We will go to some more example, all right? So that's the exponent part. The mantissa part, this is a sequence of 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, blah, 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 up to the end. Right. Bear with me first. It's just a series of this addition. Start from 1 plus 1/2 plus 1/4 plus 1/8. If this bit has 0 in it, it means that it starts from 1/2 and go forward. The first bit, if it's a 0, means I don't add this. If it's a 1, then I add this. If it's a 0, I don't add this. Again, if it's a 0, I don't add this. So you get the sequence of 2 to the negative n, 2 to the negative n, multiplied by that bit. That bit can be a 0 or a 1, a 0 or a 1. Right. This looks confusing, so let's use some example to hopefully explain things. Okay? Now, let's say I want to represent 1.5 into a floating point number. I know that 1.5 is what? 1 plus 1/2, right? So it means that if I want to do the formula earlier, the sign bit has to be 0 because I want a positive number. Sign bit is going to be 0. The exponent, I want to make sure that my number is multiplied by 2 to the 0. Because it's basically mantissa multiplied by the exponent. All right, so the exponent has to result at the end of the day is 2 to the 0. This part is 1e minus 127. So I want to make sure the exponent bit minus 127 equals 0. So my exponent bit has to be 0, 1, 1, 1, 1, 1, 1, 1. So this is exactly 127. Yes. So that's the bit in the exponent part of your number. So your floating point, right? Your floating point number will consist of 3 parts. So this is basically, let's say it's a 32-bit floating point. This is a 32-bit thing. The top bit is going to be the sign bit. Then the next 8 bits, will be the exponent bit. So you take that 8 bits, convert to a decimal number, you subtract 127 from it. That becomes the multiply 2 to the that thing. So in this case, you want the exponent to eventually become 2 to the 0. So you want e minus 127 to be 0. You want e, which is this guy, to be 127. For the mantissa bit, right? For the mantissa bit, which is this part, so that's a mantissa. Again, it's always start with 1. In this case, what do we want? We just want 1 plus 1/2, right? So we just want the first number. And we don't want the rest. We don't want the rest. We don't want 1/4. We don't want 1/8. So this bit becomes, I want 1/2. I don't want 1/4. I don't want 1/8. I don't want 1/16. I don't want 1/32. I don't want anything else. So the mantissa bit is just 1 and followed by a bunch of zeros. All right. I'll do 3 more examples. So let's do 1.25. 1.25 is essentially the same as 1.5, but the only difference is the mantissa bit is 1 plus 1/4, right? It's not 1 plus 1/2. Exponent bit is going to be the same. That works for me. I just want to multiply by 1, right? So in this case, 1.25 exponent bit is going to be 0, 1, 1, 1, 1, 1, 1, 1. Mantissa bit, do I want 1/2? No, so I start with 0. Do I want 1/4? Do I want 1/8? No, so I just do this. And for the sign bit, it's a positive number, so it starts with a 0. Sign bit, exponent bit, and then the mantissa bit. Now, I have 1.25. What if I want 2.5? You know that 1.25 multiplied by 2 is going to be 2.5, right? So in this case, I can keep the same mantissa bit. I just want to multiply by 2. How do I quickly do that? Can I change the exponent bit to become, instead of 127, I make it 128. If I make it 128, 128 minus 127, that's 1. So I multiply everything by 2 to the 1. So in this case, 2.5 exponent bit become 1, 0, 0, 0, 0, 0 for the exponent, right? And you know that 10 is 2.5 multiplied by 4, right? 2.5 multiplied by 4. So in this case, is of exponent bit of 1. You want the exponent bit of what? Or you add 2 more to the exponent bit. So that you multiply the whole thing by 4. So it's going to become 1, 0, 0, 0, 0, 1, 0. I'm losing some bits here, sorry. Okay. Okay. So that's how floating point work. Let's go through some more exercise and this part. So once we are let's do like a 10 minutes break. After the break, I'll ask you to get the binary, the 32-bit floating point for negative 1.5. All right. And then what should we do? 0.5. And then number 3. Okay. The last one will be funny. Yeah, 3. Actually, not that bad, 3. If you look at some of the example, you can change it. This is 1.5 multiplied by 2, right? Okay. So let's take a quick break. We'll come back, all right? And then we'll continue with some more example of this.